This video is on the eccentricity and planetary motion, and in this video I want to show how the eccentricity is related to the what's called the aphelion distance and the perihelion distance of planetary motion. And so what I want to do now is show the relationship between the eccentricity and the shape of the ellipse. And so for this particular ellipse, the A distance, or the distance from the center to one of the two vertices, is 10, or the distance from here to here is 10. And then C is the distance from the center to one of the two foci, is 5. So the distance from here to here is 5. So by definition, eccentricity is defined as C dividing by A. So it would be 5 divided by 10, which is 0.5. And recall that for an ellipse, the relationship between ABC is A squared is equal to B squared plus C squared. And then what I want to do now is make the eccentricity approach 1. And we'll see what happened to the shape of an ellipse, because C is always going to be less than A, because C is the distance from 0 to the focus, and A is the distance from 0 to the vertex. And so this ratio right here, C over A, is going to be between 0 and 1. And so I'm going to make it approach 1 and see what happened to the shape of the ellipse. So here we have an eccentricity of 0.9. And here the eccentricity is 0.99. So we can see that the ellipse is becoming more elongated, or become highly elongated. So let's move even closer to 1 for the eccentricity. So the eccentricity is now 0.999, and we can see that the ellipse is very flat, or it's very elongated. So the closer I move the eccentricity to 1, the more elongated the ellipse becomes. And so that's what we're seeing. When E is moving closer and closer to 1, the ellipse will become more and more and more elongated. And now let's move the other way. Make the ellipse move closer to, make the eccentricity move closer to 0. So here's the ellipse with the eccentricity of 0.1. And we can see that it's very circular. And now let's make the eccentricity even smaller. Here the eccentricity is 0.01, and we can see that it's becoming even more circular. And so here the eccentricity is 0.001. And here's the eccentricity at 0.0001. So we can see that it's becoming even more circular. And so in summary, the eccentricity, when it's closer to 0, then the shape of the ellipse will be will look like a circle. But when the eccentricity is approaching 1, then it become extremely elongated. And now let's look at an example of the example of Halley's Comet. And so what I want to do now is talk about the perihelion distance and the aphelion distance. And so here we have the ellipse. And here's focus number 1, here's focus number 2. And then we normally call this point right here, this is vertex 1, and this is vertex 2. The distance from the center to one of the two vertices, we call it A. The distance from the center to one of the two foci. We call it C. I'm going to call P the distance from focus number 1 to vertex number 2. So from here to here is going to be P. And then I'm going to call the distance from focus number 1 to vertex number 1 Q. So from here to here is Q, from here to here is P. And so notice that Q plus P is going to be the distance from vertex 1 to vertex 2, which is 2A. So P plus Q will be the distance from vertex 1 to vertex 2, which is the same as 2A. And then P minus Q is going to be the distance from F1 to F2. So we're taking this segment right here and then subtract from it this much. And we get the distance from F1 to F2, which is 2C. Eccentricity is defined as the ratio of C over A. But C over A is the same as 2C over 2A. 2C is P minus Q. And then 2A is P plus Q. And so eccentricity can also be written in terms of P and Q. And then also notice that 2A is equal to P plus Q, and so A will be P plus Q over 2. And then C will be P minus Q over 2. And now let's look at the example of Halley's Comet. And so if we place the sun right here at the origin, and then this is Halley's Comet's orbit. Its perihelion distance, or the distance when the comet is closest to the sun. And so when the comet is right here, then this distance right here, we call this the perihelion distance. Or we say that the comet is at perihelion. And then when the comet is at this position, then it is said to be at aphelion. And so the aphelion distance will be the distance from the sun to vertex number 2, which is approximately 5,200,000,000 kilometers. And so Q would be the perihelion distance. P is the aphelion distance. And therefore the eccentricity for Halley's Comet's orbit around the sun is going to be 0.96671. And so here we have 5,200,000,000 minus 88 million. And then down here just the sum. And so we can see that the eccentricity for Halley's Comet is very close to 1. And so that's why Halley's Comet's orbit around the sun, the ellipse here is highly elongated. And so that's for Halley's Comet. And then now I'm going to show how we got the polar equation, for the orbit here. And so we have just seen that the eccentricity for Halley's Comet is 0.96671. And then here's the orbit. And then this is the sun right here. And then, as I mentioned earlier, A is calculated as the aphelion distance plus the perihelion distance dividing by 2. And so for Halley's Comet, A will be 2,644,000,000. And then this is the polar equation for this ellipse. It's 1 minus e squared times a dividing by 1 minus e cosine of theta. And so we can see that Halley's Comet's orbit is a very, very large ellipse. And then the next time that the comet is going to be at perihelion, meaning when the next time is at this point right here, closest to the sun, it's going to be on July 28, 2061. And then the other planets, and so the perihelion distance for the Earth is 144,095,000 kilometers, and then the aphelion distance is 152,100,000 kilometers. And so calculating the eccentricity for the Earth's orbit around the sun, we get 0.0167. And so the Earth's eccentricity is very close to zero, and so that's why we see that the ellipse here is very circular. And then here's Mercury. Mercury's eccentricity is 0.2056. And then Venus, its eccentricity is 0.00675, which is very close to zero, and therefore the orbit we can see is very circular. And then here's Mars. And you can see that Mars, the orbit is very circular also, and therefore the eccentricity should be close to zero. And so in this case for Mars, the eccentricity is 0.0934. And then for Jupiter's, the eccentricity is 0.04866, which is very close to zero. And so again, we see that the orbit is very circular. And then here's Saturn's. Saturn's eccentricity is 0.05201. Again, very close to zero, and therefore the orbit is very circular. And then here's Uranus. Uranus is also a very circular orbit because its eccentricity is 0.046859. And then here we have Neptune's. It's extremely circular. The eccentricity is 0.009724. And then the last one we have is Pluto's. Pluto's eccentricity is 0.24442. So we can see it's somewhat elliptical right here. And so, in summary, the relationship between the eccentricity and the aphelion and perihelion distances is this formula right here. And that's the end of the video.